A growing issue is the security of communication in general. And one of the threats right now is quantum computing. There's a lot of uncertainties about the strength of protocols with respect to the capabilities of quantum computers. And I will talk about that, about the evolution towards quantum safe computer and internet security. And I will talk also about a complementary topic, the safety. So with quantum computers, we will have communication of quantum data. And I'll talk about the safety of the quantum data communications.
Welcome to talk.cybercni.fr.
Welcome to Talk Cyber CNI, the monthly cybersecurity speaker series. Today again in the regular interval, so last Wednesday of the month. We are very happy to have you today with us for a great topic. You heard it already in the trailer. We have Michel Barbeau. He will tell us today something about quantum computing. A very important topic in the relation to cybersecurity, but he will tell us much more in his talk. But as usual, before we start, Alex will introduce us to the tooling that we'll use for your questions. So Alex, I hand directly over to you. Ash. Perfect. Thank you very much. Yeah, so as usual, ask as many questions as you have, because then we have a lively discussion at the end. You can also upvote the questions in the Slido, so it's definitely a good idea to do second screen to connect to the Slido in parallel to have a look, answer the poll, and then afterwards when you go to the question tab, then you can ask your question and you can vote up and down also questions that are already in there. So that brings us to today's speaker, and I'm extremely happy to welcome Michel, because Michel and I, we worked together for 5 years, for quite a while already, and it's always a great pleasure. And Michel is always a great and huge source of knowledge, and he's working in that relatively new field of cybersecurity with quantum computing for quite a while, and therefore I'm super happy to welcome Michel today. So Michel is a professor of computer science. He got a bachelor degree from the Université de Sherbrooke in Canada. He has a master's and PhD in computer science from Université de Montréal. And from 91 to 99 he was a professor at Université de Sherbrooke. And during the 98 and 99 academic year he was a visiting researcher at the University of Aizu in Japan. Since 2000 he has been working at Carleton University, the School of Computer Science, where he's also the director at the moment. I think it's you still hold the position, which is also a lot of work. Therefore I'm even more happy that you found the time today for interacting with us. Michel's current research interests are computer networks, architecture and protocols, underwater communication and networks, flying drone networks, quantum networks, and networked control systems. So he works with really cool topics, which might even lead to another intervention a little bit later in the series. But today we have him for the quantum computing topic, so quantum safe and safe quantum data communications. Michel, I hand over to you, and we're looking forward to your talk. Oh, really? Then let's try to fix that. Okay, so I'll check that. Let me just check. Can you say something? I don't know, normally the sound is here. So I have actually no clue how it could listen only to me.
Now I have no sound. Ah, yes, it's okay now.
It's okay now. Test.
1, 2, 3, 1, 2, 3.
Okay, it works.
Okay.
It works, but nothing changed. Okay, good. Then I put the other headphones again. Okay, so we have no clue what the technical difficulties were, but you could hear me at least. But maybe Alex, maybe you do just a quick intro of this leader again, and we have that, and then I'll properly introduce Michel again, and we start with his talk. So I'll just. So will you give the intro again, Alex?
Okay, yeah,
leader?
sure.
Perfect.
So thank you everyone, and thank you for your waiting with small technical difficulties. Again, we will use the Slido tool for asking questions and proposing you a multi-choice, multiple answers poll about around quantum computing. So you can click on the link on the YouTube chat to access this tool, but you also can ask your questions in this chat, and we will answer them at the end of the presentation. Back to you, Mark Oliver.
Good. So yeah, then back to me. So yeah, sorry for the difficulties, as Alex said, and you heard me as Alex said, which is ultra weird to me because I have no clue how that could work. But okay. So, anyways, let me do the introduction again. So today we have Michel Barbeau, and he'll talk about quantum safe and safe quantum data communications. And you heard the abstract already in the intro. And Michel is a professor of computer science. He got a bachelor from the Université de Sherbrooke, a master's and a PhD in computer science from the Université de Montréal. And from 91 to 99, he was professor at the Université de Sherbrooke. And during 98, 99, he was a visiting researcher at the University of Aizu in Japan. And since 2000, he is at Carleton University, the School of Computer Science that he is currently directing. His current research interests are computer networks, architecture and protocols, underwater communications, and networks, flying drone networks, quantum networks, and networked control systems. Michel, we are looking forward to your talk, and we hope that we finally can hear you.
Okay, bonjour tout le monde. I hope you can hear me. So again, my name is Michel Barbeau. I'm a professor at Carleton University. I will give my talk today in English, but you're welcome to ask questions in French if you prefer. So my talk is about quantum data communications. Actually, I've been in computer science for 40 years. And my main topic of interest is computer networks, protocols, architecture. And this field of interest took me to quantum networks. And for the last 6 years, I studied quantum computing, quantum networks in more details. And today I'll share my experience and my thoughts about quantum computing and quantum data communications, and about the security aspect of quantum data communications. So my talk is, you don't have to be an expert. You don't need to have background in quantum computing to follow my talk, because I'll give a short background. I hope you can see my slides. I'm on slide number 2 right now. So I'll give my talk is divided in 4, and I'll start with a brief overview about quantum computing. I found that for beginners, I teach quantum computing also in my university. I have a course that is taken by graduate students, master, PhD, and also 4th-year students in computer science. And I found that when you start with looking at quantum computing, there are 2 challenges. One of them is the model. It's a different way of thinking. It's a different approach for solving problems. It has a unique model, a unique way of thinking. So that's one thing. It takes a little bit of time to get into that and become comfortable with the model. And another issue is the notation. So you have to takes time to become familiar with the notation of quantum computing. And at the beginning, I will avoid the second challenge, the notation. I will explain things without fancy notation. And we will get progressively into the notation for quantum computing. Okay, I'll talk a little bit about applications of quantum computing, applications I found interesting. Some of the challenges we have, in particular with respect to the security of quantum communication. And I'll talk a little bit about my research, how I approach the problem of doing safe quantum communications. So the work I'm going to present today, it's a combination of several things I have published already in papers. So mainly the 6 papers that are here. I'm not going to focus on one paper in particular. but I took a little bit of from each paper. And I would like also to thank and acknowledge all the people who collaborated with me on the topic so far. So their names are here. Okay, now let's talk about, let's start with the introduction about quantum computing. So I call that quantum computing for dummies, no offense. I wanted that to be simple and accessible. And I think anybody with some background on classical computing will get the main ideas of quantum computing. So the main concept in quantum computing is the qubit. Okay, so the qubit in classical computing, the unit of information is the bit. In quantum computing, the unit of information is the qubit. Now, everybody in quantum computing will say, okay, a qubit, it's simple. It's a unit of information where we can have at the same time 0 and 1 in the same unit of information. Yes, this is easy. I don't think it's very hard to understand. But the complexity comes when you combine them and when you start thinking about what you can do with them. So just let's clarify what a qubit is. Okay, I have a probabilistic interpretation of it. So the term superposition is used. So a classical bit is 0 and 1. A qubit is a 0 and 1 at the same time. And there is a probability attached to each of the values 0 and 1. So here we have a table. On the first column, we have the probabilities, P for 0, 1 minus P for 1. Okay? And a qubit, you don't really know what exact value, what the exact probabilities are until you actually, you don't know exactly what exact value it will take until actually you measure it. And when so measuring is the equivalent of reading, but we use the term measure because we can read only once. Okay, so that's one property of quantum computing. It's single read. You create a qubit, and you measure it, and the measurement is destructive. The life of the qubits ends there. Okay, one of the challenges right now. So this is a theoretical concept. And one of the challenges in quantum computing right now is actually implementing that concept and implementing stable qubits, okay, qubits that will keep their state for a long time. It's not a problem entirely solved right now. So we have superposition, destructive read, and we also have the fact that a qubit can be read only once. So what is interesting is when you can combine qubits together. Okay, and I have a generic example here. If you combine n qubits together, you have 2 to the n possible measurement outcomes. Okay, they are listed in the right column here. And each outcome has a probability. Okay. So again, it's the read is destructive. You can read that only once. You cannot clone a state like that. And it's the challenge right now is implementing sufficient qubits, a sufficient number of qubits such that they are stable, and we can address significant problems with them. One thing I would like to highlight here, one of the concepts of quantum computing is, it's called quantum parallelism, okay, or quantum concurrency. If you compare with classical concurrency, okay, with quantum concurrency, all these values exist at the same time. And they will stop existing when you do the measurement. But until you do the measurement, they all coexist at the same time. With classical quantum computing, classical concurrency, all these values, they exist at the same time, and so you can do you can launch a task concurrently with others for each of the possible values. And when you actually read one value, the result of one task, you don't destroy the others. Okay, so it's not, we have a form of concurrency, but it's not the same as classical concurrency. Another important concept in quantum computing is entanglement. Okay, so what does entanglement mean? It means deeply involved. And a good example I found to explain the concept, it's well known that elderly couples, one dies, the other one will die soon, and it's called the broken heart syndrome. So there is some form of relationship between them that is established. And it's the same thing with when you create a quantum state with several qubits, they are entangled together. So they interact together, they become deeply involved. And when you measure them, the measurement will be done in a coherent way. Okay, so according to the probabilities that are defined and that are set. And the great thing about that, and it's something exploited in quantum communications, quantum networks. So you can entangle two qubits, okay, and then you separate them across distance, and the entanglement will persist between them. Okay, so this is a property that we don't have in classical computing, entanglement of bits. So this is something new. Now, another aspect of that, so I explained what a qubit is. The qubit is the basic unit of information. Combining qubits, you can create quantum states, quantum complex states that can represent your problems. But how do you actually do computation? Okay, and this is one of the hardest part of quantum computing is transforming an idea to something that can be done by a quantum computer. And everything is done by transformations. So I use transformation here, but you can also say gate, operator, matrix. These terms are more or less equivalent. Okay, so the general idea is pictured here. On the left, you have a quantum state, okay, an n-qubit quantum state, as I defined before. We have the probabilities, and we have the 2 to the n outcomes. Okay, the right arrow represents a transformation. And all transformations, gates, operators, they do that. Okay, so they reshape the probabilities, okay, in some meaningful way, according to the algorithm you want to implement. So often you can start with a uniform probability distribution for all values, and the transformation will make some outcomes more probable. Okay, and when you measure these more probable outcomes are your results. Now, again, this is the challenge when you have to solve a problem is to find this transformation. You're limited. You cannot do everything. And implementing that is a challenge also, like implementing a quantum computer that can do any kind of transformation, any kind of theoretically possible transformation. It remains a challenge in quantum computing. And also, I mentioned that states are not stable. So errors can be introduced because states are not stable. And errors can be introduced by gates themselves also, because they are not perfect. So there are various constraints. Okay, so that was my introduction to quantum computing. So let's have a look now at some of the application. I picked two of them. Okay, so one of them is quantum key distribution. It's a well-known application, QKD, the abbreviation. It's not new. It's been around for almost 36 years, and it had been introduced by Bennett and Brassard, two researchers. So what QKD does, there are two parties, and so when you read things superficially, the protocol establishes a secret between the two parties, A and B, let's say, okay? So to do that, the QKD uses two channels, a quantum channel. So this quantum channel transports photons, and each photon embeds a quantum bit, let's say, a data bit. Okay, so it uses, so that's the quantum feature of that, the use of a quantum channel. In parallel to that, it uses a classical channel. And the assumption is that the classical channel supports authentication. So this is a protocol that is not new. Several improvements have been proposed to it. I did there is a hardware available on the with some equipment providers, and you can actually for a few $1,000s implement a version of it. There are several challenges in the implementation of it. So in for the photon channel, the assumption is that you can control single photons. And this is not easy. It's not something that physicists can do easily right now. It's still a challenge. So there are many adaptations to overcome this challenge. Many adaptations have been developed. Now, if you look at carefully at the protocol, soon you'll realize that actually it's not a key distribution protocol. It's a key expansion protocol. Okay, so for the protocol to work, the two parties, A and B, they need to pre-share a secret. Okay, so actually, although many extensions, many adaptations have been introduced, supporting QKD is still a challenge. And I was reading recently that the National Security Agency in US decided not to recommend the use of QKD. They give a long list of, in fact, 5 reasons. One of them is, one of the reasons is the one I just explained, the fact that it's not a protocol that is autonomous in itself. It needs classical support of classical security. And another of the reasons they gave is the need for special hardware to support that. So for the photon channel, so you need optical fiber and you need hardware that can control. At least they are not able to control easily single photons, but they are able to control weak laser pulse photons, weak laser pulses of photons, actually pulses that contain a low number of photons. And there are other reasons also that have been given. But so this is just one opinion, NSO opinion, the NSO opinion, but you will find commercial products of that. And you will find also other organizations that believe in QKD and that have plans for using QKD. Another application that I found very interesting, quantum machine learning is a very hot topic right now. We all know that. And there is a quantum version of it. Okay. So, and there is hardware being developed. There are companies working on that. There's some research ongoing. So I will explain the things simply. And it gives me an occasion also to start introducing the notation for quantum computing. Okay, on the right side, one of the ways to explain or to describe an algorithm in quantum computing is with a circuit. Okay, so you can describe an algorithm with equations, and actually the equations can be very compact. And an equivalent format is the circuit representation. And you have an example on the right. I would say the way we develop algorithms right now in quantum computing, we are, if we compare with classical computing, we are at a level where we were after the Second World War. Okay, so before the introduction of high-level programming languages, there are languages, there are programming languages, there are many programming languages that support quantum computing. But in my opinion, when you actually work with them and try to do something, you actually realize that it's actually, the quantum part is actually very low level, okay? And very detailed compared to what we can do with normal computing right now. We have programming languages with very sophisticated abstractions. We are not at that stage with quantum computing. So on the left, you have an example circuit. So each horizontal line represents a qubit, and each box represents a transformation that you do on the qubit. And there are vertical lines connecting horizontal lines, and these vertical lines make the qubits interact together. Okay, so entanglement will be created between these qubits because of these connections. On the left side, okay, so in terms of mathematical notation, for quantum computing, we use the kit notation. Okay, so vertical bar, a symbol. So here I use psi, the Greek letter psi, psi 0 to psi 1, and the greater sign. Okay, so ket psi 0, ket psi 1, ket psi 2, they represent individual qubits. And the, the circuit, so this is my arrow of the previous slide. So the circuit implement a transformation shapes or reassign probabilities of the initial quantum state. And at the end, on the right, you have a resulting quantum state that you can measure, and the measurement will mean something. Now, I'm skipping many details, but what the main idea of quantum machine learning is here on the first point is what quantum machine learning does, the quantum circuit is variable. It has variables. So these variables are represented by the omegas here. And quantum machine learning is just about training the circuit. So finding the values for the variables in the circuit such that the circuit outputs something that we want, that is meaningful for the problems. Okay, so it's about training a variable circuit. So normal quantum circuits are not necessarily variable. So this concept is used specifically for machine learning. There are many things I found very exciting about machine learning, quantum machine learning. One of them is the way you encode data for machine learning. Several forms of encoding are possible. One form I found particularly interesting is encoding the information and the probability that so the information is not directly in the qubits, it's in their probability. And I like that because the representation of the information is extremely compact. And also I talk about quantum parallelism. It's something that quantum machine learning uses extensively. So once train a quantum circuit is very efficient, very fast. So I like that very much. There are papers several papers that have been published about quantum machine learning. One of the things, okay, that I think also is promising. So we saw that quantum computers can do things that classical computer cannot. Entanglement is one of them, okay? So quantum computers are not the same as classical computers. So maybe there are things we can learn, that quantum computers can learn, that classical computers cannot. Okay, this is one of the hopes with quantum machine learning. Unfortunately, today, I cannot point you to any evidence that or any concrete example that this actually happens. So question mark, this is an open problem. Another thing is, quantum machine learning is very efficient once you have the data in the quantum format, okay? I did a few examples, and you can look at the details in my papers. One of the problems that I highlight is the cost of interfacing quantum machine learning with the classical world. So it means that if your data is in the classical format, there is a cost of mapping the data from the classical format to the quantum format. And this cost right now kills all the benefits you get with quantum machine learning. So there are solutions to that. Sensing data directly in the quantum format is one of them, but it's still an open question. I don't have a clear answer for that problem. Okay, now I'm going to focus more on security. Some of the security challenges. Okay, in my title, I say safe quantum, quantum safe. This is maybe a little bit confusing, so I'll clarify here what I mean by that. Quantum safety first, okay? So one of the concerns associated with quantum computing right now is that theoretically, quantum computing can break the current computer and internet security, RSA. And the reason for that is that there is an algorithm, there's a quantum algorithm that can factorize into prime numbers any number. And there is so I'm referring, of course, to the well-known Shor's algorithm. And more recently, there's a paper by a group, Wang et al., that have demonstrated prime factorization also on the D-Wave computer. So theoretically, quantum computing is a threat for classical cryptographic algorithms. And quantum safety means cryptographic algorithms that cannot be broken by quantum computers. Right now, maybe in the later, but right now we don't know if they can be broken by the quantum computer. We don't know how to do that. Now, another thing that I have addressed is in my research is safe quantum communication. So quantum safety is mainly about classical data, the threat of quantum computing for classical data. Although with applications such as machine learning, so we will have quantum data, and eventually we will have quantum computers that will be distributed, that will collaborate together, and that will exchange data. So this is quantum communications and networking. So there is, I found that there is often the misconception that because it's quantum, we don't have to worry about the security. It is secure by nature, by construction. And this is not true, okay? So quantum data is not secure by nature. It has nice properties. But as we saw in the example of QKD, and I can give other examples, all quantum communication protocols they rely on classical methods. These classical methods are not necessarily quantum safe. That's one thing. Qubits interact with their environment, so they are sensitive to perturbation. They can easily be disturbed, and so they are not safe by nature. Okay, and it's a problem that needs to be addressed. Okay, I'm going to here explain the same problem, but in a different way. We have a table here, 2D table. So I'm on the left, vertically, we have a line for classical data, and we have a line for quantum data. Horizontally, we have a column for classical cryptosystems, and we have a column for quantum cryptosystems. Okay, let's go with this cell first. This is the easiest to understand. So we have classical data, bits, packets, messages, data structures made of classical bits, bytes. And there are several classical cryptosystems available for security, to secure them. So I made a list of 5 classical techniques. And I added here post-quantum cryptography. So one area of research that is very active right now. So we talk about the quantum threat for classical methods. So there's an area of research called post-quantum cryptography. So it's about creating new cryptographic methods that are resistant to the quantum computer, that cannot be broken by, at least with the knowledge that we have right now, that cannot be broken by the quantum computer. Okay, and it's I would say it's a direction that I talk about the output of NSA about QKD before, and it's the direction that they favor right now to address the quantum threat using using post-quantum cryptographic methods. Simply because in terms of there's no special hardware needed to support them, cost is much lower, and they can be supported by classical computer, classical communication hardware. There's no, in terms of investment, it's much less. Okay, now here, okay, classical data, quantum cryptosystems. So it's an area of research, I would say, that started 36 years ago with QKD, that evolved. There are survey papers that review all the work that have been done with QKD. QKD is initially discrete variable. There are continuous variable version of QKD. There are weak laser pulse implementation of it. So this is about using quantum techniques, quantum technology to secure classical data. Okay, I think it's worth. It's still work considering that. There are very nice properties. I would say not all problems have been solved. There are still problems, issues to be addressed. Now, I'll expand a little bit about what we have here, okay? So we talk about potentially interesting quantum applications like quantum machine learning. These applications involve quantum data. I said few words about that quantum data need to be secured also. And so data is quantum, so we need quantum cryptosystems to secure them. Not a lot of research has been done about that so far. I listed a couple of authors here. You will find the exact papers in the exact references in my papers. And I will explain now a little bit how this works. And this will be the last part of my talk. So how we approach that, okay? So I presented that several times before, and I found that it's not obvious. First of all, why we need that, and second, why, how it works, what it involves exactly. So I'll not go through a great level of details. I'll give an overview of how things work. Okay, so I'm going to give an example with quantum message authentication. Okay, so I assume you all know what authentication is. So it's about verifying the identity or the integrity of data. Okay, so making sure that data has not been altered in this case. But the thing that is unique to what I'm presenting right now is that the data is quantum. Okay, so how to authenticate data in the quantum format. There are several, I explained some of the constraints that we have with quantum data. We cannot clone it, so we cannot take copies of quantum data. We have to take that into account. So there are unique features that require unique solutions. And the idea I'm going to explain here, so you will recognize some concepts, some ideas that are used in classical message authentication, but in a quantum flavor, with a quantum flavor, okay? So, I have a scheme for the authentication of a message. So we talk about quantum communication. Quantum communication means that we send a message from a source to a destination. The message is represented here in the ket notation, ket psi. It's an n. Let's say it's an m qubit quantum state. Okay, representing some information. Now, to build a packet, we add a suffix. Okay, I had a sequence of d qubits initialized to the state 0. Okay, so this is what is represented here. It's a sequence of d qubit in state 0. So it's a placeholder for the signature. So the packet message placeholder for signature. Now what we do, okay? So we use an operator. So operator transformation, I mentioned that. I gave a generic example of that. So we use an operator, but an operator that has nice properties. So I don't show everything here, but one of the nice properties is that we can map a classical key to this operator. Okay, so the operator is the secret here. But actually, in this technique, so we use a Clifford operator. And the nice thing, so Clifford operators have nice properties. So one of the things is it randomizes it maps unit transformation to other transformations, but in some randomization form. So it scrambles the transformation, if you will. So that's one property. One of the properties, the other properties that we use is that we can map a classical key to an operator. So we have an interface. So although we have in the quantum world, we have an interface with the classical world. Okay, so we use this kind of operator to map the packet to a new format and a new quantum state. So it's just a transformation. We don't read, we don't measure, we just transform the state to another state. And this transformation will alter the content of the placeholder. Now the attack model for this. So this is the packet, we send the packet. So the only significant thing that an adversary can do is to transform the packet to something else. Okay, this is our adversary model. And with this mechanism, we have the possibility to detect the attack. And it works like that, okay? So S prime, so S is what we send. During the transport, an adversary can alter the content. So we receive something called S prime. So S prime is the combination of M data qubits and D signature qubits. So when we receive that, okay, we reapply the operator. Clifford operators have nice properties. So if you apply the inverse, so you cancel their effect. And this is what I'm representing here. And at the end, so you measure the signature qubits. And if the value that is there has not changed, so initially we put 0. And if you all read zeros, you assume that the communication went fine. And if you read something other than 0, so it's an indication that an alteration happened during the transport. Okay, so I wanted to give you an idea of how to address quantum, the security of quantum communication, the issues that we have. And this is my conclusion, my general conclusion about what I presented today, also about my experience overall with quantum computing. There's no doubt that there are potentially very interesting applications. There's no doubt about that. Number two, I highlighted that because of the algorithms that can eventually run on quantum computers, classical computer and internet security can be broken. So it challenges classical computing right now. And quantum computing, also number three, has its own challenges. I talk about the difficulty of learning the model initially. There are quantum computers available right now Some of them can be, you can try them on the internet. I did a couple of examples. And my experience right now is with quantum computers is that the stability is not there. So when you solve a problem and you want to run the solution, your problem and get a solution, you actually have to run it several times to obtain a result that is consistent. Because of stability, they need to be recalibrated often, and the error rate right now with quantum computer, at least with my experience, is very high. Okay, so implementing is still a challenge. Another problem issue I found right now in quantum computing, it's like there are two main groups of people. There are the theory people, okay, that assume perfect qubits that have no errors, and they develop algorithms under this assumption. And there is the other group of practical people that try to make it work, and to make it work, they make some compromises. So there is a distance between theory and practice, and I'm sure this distance will remain for a long time. Okay, and the last challenge is doing with quantum application is the security of quantum data, mainly because quantum protocols are not self-sufficient. They need classical methods, and the threats that exist for classical methods, they also exist for quantum data. Okay, so I can take your questions.
Great. So thank you very much, Michel, because I really loved it, because it's a complicated topic, and you managed to give us some insights in how it could be. And so in the series, I always take the chance of asking, or the chance of asking the first question. And so my first question is, why do we have quantum computing now? So what happened that quantum computing is now an issue and it was not an issue, or now has a breakthrough and didn't have a breakthrough like 10 years ago, or maybe it did have? So do you have an answer to that? What were the events that were happening now? Why is it gaining more pace now? At least this is the impression that you get when you read the media. Yeah. Maybe you can give us some source to that.
I think it's getting pace right now because of recent technology of advancement. I think if we take the two examples that I considered in my presentation, QKD. QKD had been very abstract for a long time, and I was when I start looking at this, I was actually surprised to find that for a few $1,000s, you can buy some optical hardware, and with a little bit of hardware skills and software skills, you can actually implement it without being an expert in photonics or anything like that. And this is I would say the system I showed in my slides. It's an amateur system, but there are much more advanced systems that are, even though they don't implement QKD as defined in the original paper. That is, so theoretically it's extremely secure. So we don't have theoretically the same level of security, but in practice it's extremely secure, the implementation. And even the few $1,000 implementation I did, to be able to break the system, you have to intercept the laser pulse. It's doable. We have the hardware for doing that, but it's not compared to classical, let's say, wireless communication. With classical wireless communication, you spread when you type something on your keyboard and it goes over the air. It goes in all directions. With a laser beam, its focus, it goes in a confined physical space. For machine learning, same thing. You can actually, although it's not a perfect world yet, but actually you can write the examples, you can run examples on quantum computer. So it works, it runs, although it needs to be perfected.
So to summarize your answer, it's like there were advances in the technological direction and possibly also a little bit of spreading, that you have multiple companies now that are looking at it, it's getting more available, and therefore it makes a lot of sense that it's now more present in media. Yeah. Very good. So yeah, Alex, which questions do we have in the audience?
Thank you, Michel, for your presentation. We have lots of questions regarding more in general the quantum computing research area or technical area. So I will try to regroup them into big questions or meta questions. First ones are about the fact that can we emulate quantum computers with our architectures, with what performances? And the second one, which is linked, is can I play with quantum computing at home? How can I learn the basics of quantum programming?
Okay, the first question, can you emulate quantum computing with classical computing, I guess?
Yep.
Yes, of course. You will find several simulators on the internet, actually, that you can download on your computer and you can run on computer. I tried several of them. It's very good to learn. But what I found is that it's just an indication. But I found that when you try to handle a problem that comprises more than 4 or 5 qubits, you face a performance challenge. So it can take days to get the response because the classical computer keeps explicitly all combination. In the one of my slides at the beginning, I explained what a quantum state is. So with n qubits, you have you have a superposition of 2 to the n values. So the number of values you have to maintain grows exponentially with the number of qubits. The nice thing about quantum computers is that you have native support for that. The hardware supports that. With classical computing, all these values have to be maintained explicitly. Okay. So you very soon reach a problem of memory and time complexity. Although it's doable, it's nice. You can try, and you can learn.
Okay. Do we need new programming concepts for the quantum computers? Do we need new programming languages? Do we need new concepts within these programming languages? Will they offer us more features that are not captured in today's programming languages?
Yeah. What I found, if I can give an indication to that, what I found I looked at several quantum computing languages. I have example in my programming examples in at least one of my papers, and they are available on my GitHub page. And I found that um, what they do, so they take a classical programming language, let's say, for instance, C# or C, and they integrate in the language the low-level programming concept of quantum computing. So gates, qubit, line, and so what I've seen so far, my understanding and my interpretation of what I've seen so far. So quantum computing languages, actually what they do, they embed quantum computing concepts rather than being new languages, entirely new languages adapted to quantum computing. I think it's an area of research making with, if we look at what happened with classical programming languages in the early days, programming a computer consisted of plugging and unplugging cables on a panel, and it evolved to high-level programming languages that we have today, such as Python and Java. So I believe we will see this evolution with quantum computing. So abstraction will be created with time, and things will be made easier with time. But I don't think right now I would not say that learning quantum computing or quantum programming, it's something easy right now.
Mm-hmm. Good, thank you.
Okay, so thank you for these answers. So this brings another question. So there is still questions, but you answered partially about it. So how can we play with quantum computing at home, and how can we learn the basics of quantum programming? But you say there exist tools and it's quite difficult yet to use it. And then you said that quantum computing will maybe change the paradigm of programming or computer science. So which areas of computing will be affected by quantum computing according to you? And what new possibilities come with quantum computing and why?
Okay, so first question, how can you learn quantum computing at home? So I don't want to make any publicity for any company in particular, but two experiences I liked is so IBM has a quantum, I think it's quantum computing experience. So you can sign in and create an account, write and run programs on some quantum computers that are available on the internet. So they don't grant you access to the high-end quantum computers, but you can try and learn at least on quantum computers with few qubits. Another experience more on so this is on the general computing side. Another experience I like more on the AI side, machine learning side, is the environment of Xanadu. So xanadu.ai, it's a website. So there's software you can download, and they are very good tutorials. IBM also, they have very good tutorials for general quantum computing, but Xanadu AI, they focus on machine learning. So they have very good tutorials about quantum machine learning. So these are two things I like and that I recommend. Yeah, your second question was?
Other questions were there were a lot of questions about what will quantum computing change. So which areas of computing will be affected by quantum computing? What are the new possibilities? Will be a switch day from a classic computer to quantum computing computer? Will internet take changes with quantum computing and research? So what will bring to computer science or for the digital world, I will say quantum computing?
Yeah, first of all, maybe an answer that is general to all of this. When you study quantum computing and you go deeper and you look at the work that has been done, the algorithms that have been developed. So that this is my opinion. So maybe not all quantum experts will share this opinion with me, but this is my opinion. So one of the things I realized is that compared to classical computing, there are many constraints. And actually, I believe that not all problems are amenable or are solvable eventually with quantum computing. Okay, so quantum computing is a model that works well for certain problems, and for certain others, they will not. The model doesn't work. So I think quantum computing, for sure, I don't think this will happen before the end of my life. I don't think quantum computing will replace classical computing. It will be a complement to classical computing. So eventually, I believe we will have computers, and maybe even in smartphones, that will eventually embed a quantum processor, and some of the tasks will be accelerated and will be dispatched to our quantum processor. So some tasks that can be addressed well by quantum computers. So in terms of areas that will be affected by quantum computer. So of course, I'm not an expert in all areas on all topics. I gave two examples. I think quantum computer will have an impact on quantum, on classical computer and internet security. So this will have, the methods that we use right now will have to be revised. Machine learning is one of them. And so machine learning, it's a framework with that opens the door. So if we are able to do nice machine learning with quantum computers, so machine learning has application in a large number of areas: commerce, finance, all sciences, biology, chemistry.
Okay, so there will be changes as big as with new machine learning and GPUs calculations.
Maybe let me jump in here, Alex. So so you said it will coexist. So from a cybersecurity question point of view, there's always the question of an equilibrium between the attacker and the defender. And so what would your assumption, I mean, it's a little bit into the blue, I know that, but what would your assumption be? Like, will it be that some groups that do something like attackers will buy such a quantum computer and then afterwards they be super powerful and not able to be defended? Will there be a threat in equilibrium between those having quantum computers and those having quantum computers?
Yeah, so the first organization that will make Shor's algorithm work. So this will be a serious threat for others if they are not prepared for that or not. So when you ask your question, it was a little bit interrupted.
So yeah, my question was just
I got everything right.
The question was just about the equilibrium between those having quantum computers and those not having them regarding security and attack potential. Like if a group will buy an attacker group will buy a quantum computer and then they are much more powerful and can destroy all traditional computer infrastructure.
Yeah. And I think it's a motivation for, if you look at all the investments that all the countries are making around the world, although I'm probably not the only one who understands that the quantum computer is not ready yet. I think it's a it's a threat with a certain level of risk. And what we see right now is that in America and in European countries, China, Russia, they are all investing in that to maintain the equilibrium.
So, and we also talked a little bit about applications. So I would have two interesting applications. The first one is one of the biggest threats that I see at the moment is ransomware. So people that are coming, they're encrypting your disk using classical disk encryption, and then you have to pay money in order to get the key. What in the moment we have quantum computers, what will it mean for ransomware?
Yeah, I think if something like that is doable because classical data is not secure, there's nothing. Also, if quantum data is not secure, there's nothing I can see that that can prevent that eventually. It will be done differently, but an attack like that can be perpetrated on quantum data if the quantum data is not protected. Because even if it's single read, what I can see is that so right now the adversary encrypts your hard disk, and the adversary on quantum data can easily apply a secret transformation to your data that will scramble your quantum data, and when you measure it, the measurement does not make sense.
So that means the attack, you can still use the attack also with quantum computers because it's just a magnitude more difficult to encrypt. But with a quantum computer, it will be same price. So that means the attack will still be valid. But in the transition phase, like before we all have quantum computers, I could imagine that when my traditional computer gets affected by ransomware and I send some of the random bits to someone having a quantum computer, that it might help to decipher it and to find out the key much faster.
Yes, for a while.
Okay, cool. And the second thing I was thinking about is another hype theme still at the moment, which is Bitcoin or cryptocurrencies. So what will the effect of quantum computers on cryptocurrencies and more in particular on wallets be that are based on the fact that we are using encryption functions that we cannot decrypt easily, so on the trapdoor functions?
Okay, two things about that. I know that I did not look at all the details, but there are quantum forms. So there are papers about a quantum form of cryptocurrency. I've seen that. Although I cannot explain a lot. So this is number one. Number two, I think cryptocurrency will benefit also from the research on post-quantum cryptography. So methods new methods resistant to quantum computers could be integrated into cryptocurrency.
And when you think about the coexistence of classical infrastructure with with quantum computers, would they be super efficient crypto miners compared to traditional computers? What would your guess be?
They will be what?
Or if they would be very efficient crypto miners, so if they would be able to create hashes much faster than the GPU-based processing that we have today.
Yes, I like the example I did. In my presentation with the Clifford operator, it's the analogous of the of a hash function. So with classical computing, So the Clifford can be done on a, of course, on a superposition. So when it's implemented in hardware, so in one shot, you will sign and authenticate an exponential number of states. So I think it's interesting from that point of view. Well,
And that means it would indeed affect at least in the transition phase, it would affect the system of the cryptocurrency, because the system of cryptocurrency is that everybody has the same power to create something, and therefore it's difficult to create, and you would be like the super creator, and so you could get a lot of it, and then the courses would probably crash, and even your existing wallets might have some problems there.
Okay. Yeah. I'm not an expert in cryptocurrency. I wish I could. But I think it's it's an interesting, interesting questions.
Yeah. Okay. Cool. Thanks, Alex.
Okay, back to the audience questions. So now 2 questions about more the ecological or environment issues with quantum computing. So the first one is, since it consumes a huge amount of energy, will quantum computing become an environmental problem like the blockchain before it? And the second one is, do quantum computers emit more or less radiation? Are they dangerous for the environment?
Okay, about radiation, I don't think so. Although, again, maybe it's a question we can ask to physicists. In terms of power, I've never been in physical contact with a quantum computer, but I saw pictures before, and you can see pictures on the internet. And the pictures you see for a few qubits computer, you have a huge box. So right now, I don't have scientific evidence. I don't have numbers to show, but my intuition tells me. With these huge boxes to support a few qubits, and so often they have to cool down to close to the absolute zero. So the amount of power or the amount of energy right now needed to support just a few qubits must be enormous. So I think if we keep going like that, there will be issues with the environment. But I hope and I believe, as the technology will improve and will be perfected, eventually the quantum computer will be low energy compute consumption and will fit, the quantum processor will fit in your watch. Okay, and this is not unrealistic to think that way, because it's just the kind of evolution we have seen so far with classical computers.
Okay, and so another question related to the nature of quantum computers. Why do quantum computers often use light?
Okay, why they use light? Because quantum, if you look at the meaning of quantum, quantum means unit of information, so a basic unit of information. So this is the idea behind, the main idea behind the quantum model. So you encode information in particles. Okay, so in quantum, so the quantum of light is the photon. So light is made of photons, and as far as I know, so photons are elementary and cannot be broken into smaller particles. That's my understanding of photonics. And it's maybe a naive interpretation, but it's sufficient to understand. So light is made of photon. So the quantum of light is photon. And we use light because it's actually possible, or we think it is possible, it can be done right now to a certain extent. We can encode information in individual photons, in qubits. And photons, the way it's done, it's by changing the polarity of light. So light is polarized, and you can buy sunglasses that are polarized, for instance, that will reduce the amount of light, because only photons with a certain polarity will pass through the glass. And it's the reason why we use light, because information can be encoded in particles of light in photons.
Alex, you're mute.
Yeah, thank you. Yeah. So now there were some, it remains few questions. Some were answered, but some questions were about the technology used by companies. And one question was what is the difference between the groups companies working on quantum computing today? Are they all following the same approaches, or what are the differences between companies doing quantum computing?
No, they are not following the same approach. And I gave an example with with QKD. There are several different approaches. First of all, with quantum computing, initially the model was discrete. Now there is a continuous model that is harder to understand, even harder to understand, of quantum computing. So there are companies favoring the discrete model, and there are companies favoring the continuous model. And I give an example of a company favoring the discrete model. It's IBM. Xanadu AI favors the continuous model. So that's one thing. In terms of technology for implementing, so I gave the example of light. Light can be used to encode information, but electrons can also be used, other kind of particles, and there are companies favoring other particles, other kinds of. Xanadu AI, for instance, favors light. Their technology is based on light, and IBM is I think it's on electrons, and there are other candidate particles for that.
Okay.
Do we have enough competition? And related to that, why do I not see the classical CPU companies, AMD and Intel, in the press about quantum computers?
Yeah, I think there's a lot of competition right now, and there's something called the quantum supremacy. So it's about being able to solve a faster, in short, to be able to demonstrate that we are able to solve a significant problem more rapidly with a quantum computer. So it's a big topic of competition right now between companies.
Okay. So I will just finish, I think, with my questions, and then go to Mark Oliver to the live poll, to the multiple answer questions sent to users, to visitors, sorry. So the one question was about the security. So how company manage the cost of having a security increase by using quantum computing rather than other tools where when there is a weakest link of the security chain? So is it worth it to use a quantum computing service to manage a whole security architecture, where there exist some services that are not quantum. At what cost it is interesting to use quantum computing for only specific parts of a system?
Yeah, I think it's not a question that is easy to answer. And what I would do if I had to resolve that problem for my organization, I would do a risk analysis.
Okay, yeah, of course.
So I will examine my data, I will examine the threats, and I will examine the option for for protection that are available, classical, post-quantum, eventually integrating some quantum technology. And I would decide versus cost versus risk, which solution is the, and I will look at all the material available on the internet.
Okay.
So like the NSA evaluation, it's I found that their arguments make a lot of sense, but there are other opinions on the internet you will find.
Okay, thank you. So few questions, one two-sided questions, which is interesting. So why is quantum computing good for machine learning? And how could machine learning improve quantum computing?
Okay, why quantum computing is good for machine learning? So if we come back to the the arguments I gave, so when I talk about that is, so one of the main things I think it's the speed up. So if eventually we have data directly in the quantum format, and we can do everything in the quantum environment, so we will have really big benefits because machine learning is a big consumer of computing resources right now. So if we can solve and implement things with a quantum computer, I think we will have performance benefits, although we are not there. And one of the things also, and that I hope, and as I mentioned, I don't have evidence for that, is that because we will be able to do things with the quantum computer that we are not able to do with the classical computer, learn things that so you will find this statement in many places. This is one of the expectation.
Okay.
So what machine learning can bring to quantum computing?
That's it.
So machine learning is a solution to is used to build solutions for many problems. I guess it's not something I studied particularly, but I guess it could help to solve scheduling problem, for instance. Just an idea, but I'm sure it's machine learning can help quantum computer in many ways.
Okay. And the last question, which is more open, do we need regulation for quantum computers?
Okay, do we need regulation?
As said Mark Oliver, maybe they could break at some breakpoint of the computer science or computer technology history. They could give you lots of money or something like that to break some codes. So maybe is it interesting now to make some regulations about this kind of computers or not yet?
And this would be like the negative motivation, and the positive motivation would be like, do we need regulation in the sense that the state has to push, let's invest more here, companies do it, you get benefits and so on.
Yeah, in my opinion, if we want to see the research progression in research and advancement, the less regulation we have, the better things will be.
Okay.
Good. Then thank you very much.
That's all from my questions. And then for the multiple choice answer about the
Yes.
question, what is quantum computing for you? An astonishing majority of 83% of users have answered that it could be an advantage rather than an utopia for 17% and a threat for only 33%. Of course, if you sum all percentage, you will not have a 100% because I've allowed the fact that user could make several answers at the same time. So not only one, not to have some mitigated answers and not so biased.
Very good. So we have enthusiastic people.
Yeah, that's it.
Very good. Cool. Yeah, thank you very much, Alex, and a big thank you to you, Michel. It was a great presentation with I especially like the first part with the introduction to it and explaining it, and then this great discussion afterwards where we brought it up a little bit and discussed with you. So thank you very much. I loved it. So
thank you very much for listening to my talk. Giving a talk on a tool like that, it's very abstract because you don't see the audience. But I hope I'll be able to meet several of you in person eventually.
Yes, and we hope the same. Great. Yeah, thank you very much. And we'll also have many more listeners afterwards. And so if you have questions to Michel, don't hesitate to contact us, and we can relay to him, or if you look him up in the internet, he's easily findable there, and he'll probably be happy to discuss with you also some topics there. So this brings us to the end of today's edition. In the next edition, which will be in 1 month, so it will be on the 28th of July, we'll have Hasan Akram from Matrix GmbH in Germany, and he'll be talking about something very concrete, namely automotive security. So how can we secure cars? And there he has the title, How to Make Millions in a 5 to 1 billion market. And Hasan, he's an entrepreneur that I know for quite a while, and I'm sure that it will be a super enthusiastic and super interesting talk, and therefore we look forward to welcome many of you in that talk. As usual, you will have the trailer next in the stream, and if you did not subscribe to the channel yet, please do so, and if you want to get notified when there's a new video, you have to press this bell icon. And with that said, have a great evening, have a great start of the July, and see all of you in 1 month. And please tell your friends about the series so that we have even more visitors for the next edition. Have a great evening. See you.
I'm going to talk about the risks, the brief history of automotive cybersecurity and where we're at and what could go wrong, how much power the attackers can have, what can they do in our life in terms of creating havoc. At the same time, what are the opportunities as researchers and entrepreneurs and aspiring entrepreneurs, the students we have as the listener, what are the opportunities you have to make your millions and billions out of this $5.1 billion industry?
Cher cyber-CNI, pôle d'excellence Région Bretagne. Au revoir et à la prochaine.